So that was just for the recording, everything above was just a recap from last time. And now that we're asking the question, what if instead the source of the current flow is an induced EMF rather than the battery? And so in that case, then in our circuit, yeah, so it was a recap. Then in our circuit would just look like this. There's no battery anywhere. And just to be clear, there might be some magnetic field. In order to induce an EMF, we would need to have some magnetic field that is changing inside the circuit to produce a flux. And so maybe we have that the magnetic field here, B, is decreasing. Right. So if B is decreasing into the screen, then we know that the, right. So B is pointing into the screen, the flux is into the screen. Sorry, I'm still trying to get used to this issue with the reversed camera. So the magnetic field's pointing into the screen, but the flux is decreasing. So we need more magnetic field pointing into the screen. So if we need more magnetic field into the screen, then that means that we would need a magnetic field that goes, or an electric current that goes this way. Sorry, that's the wrong way. Basically, we need to produce more magnetic field that's going into the screen. So that would result in electric field that points this way. And so if the magnetic field is decreasing, then this electric field will be induced to go clockwise. And so that will bolster the magnetic field according to Lenz's law. It will produce more magnetic field into the screen. So if we apply the loop rule here, the loop rule in this case is a lot more simple. It's just an integral. It's a closed integral over the entirety of the loop of E dot dl. And it would say that this is equal to 0. But here the magnetic field is the electric field is always pointing in the same direction, unlike in the case where the electric field is pointing in the opposite direction inside the battery. So there's no chance for this thing to cancel out with anything. So it could not possibly be 0. Because there's nothing to cancel out against. So instead, as we've already established, and we did talk about this before, the loop rule should instead read, and we've talked about this, it was a sum over the loop of delta V. That should be equal to the rate of change of flux, of magnetic flux in the circuit. And so in terms of the electric field, we can rewrite this, this equation as, sorry, there needed to be a negative sign there, but it was equal to 0, so it didn't matter. In terms of the electric field, that would give us that an integral over the loop of E dot dl should now equal the rate of change of the flux. And now this is okay, because you have something that's not 0 on the left-hand side and something that's not 0 on the right-hand side. This phi sub b, by the way, is the flux within the loop. And so what we find is that a changing magnetic field induces an electric field that circulates around it in the direction specified by Lenz's law. So you would apply Lenz's law, figure out that the electric field needs to bolster the magnetic field in this case. So the electric field circulates in that direction. That would produce the current flow in the same direction that would help increase the magnetic field to keep the magnetic flux the same. Mathematically, we can rephrase that, or rather we can phrase that mathematically. The flux through a loop, or the flux across a surface rather, is an integral of B dot dA. And so we can actually write the above expression, we can write this guy using that result to get the following statement, that the negative loop integral of E dot dl, remember this left-hand side is just the change in voltage around the loop. This should be equal to the time derivative of the integral of the surface enclosed by the loop. This is a big subscript, enclosed by loop, of B dot dA. And so then we can apply Stokes' theorem like we have before to get the following. We apply it to the left-hand side to rewrite a loop integral as a surface integral, and we get that this is a negative integral of the surface of the curl of E dot dA, that's Stokes' theorem, is equal to the time derivative of B dot dA integrated over the same surface. And so because this holds for any surface, for any loop, for any whatever, we get the following local form. We get that del cross E, the curl of E, is equal to the negative time derivative of the magnetic field. And this equation, this is also equivalent to Faraday's law. Remember, we started with an integral version of Faraday's law. This is the local version of Faraday's law. So remember, in electrostatics, before we had this notion of current flow at all, we had said that the curl of E is 0. Now we see that this just isn't true in the presence of any changing magnetic field, and in general, it won't be true for any non-electrostatics case. What this means, though, is that if there is a changing magnetic field, the electric field is no longer conservative. If you remember from, I want to say it's like 9A, maybe you learned it in math too, that a vector field is conservative if and only if its curl is 0. So by saying that the curl is not 0 here, we no longer have that the electric field is conservative. What that means then is that the electric force is not conservative in the presence of a changing electric field, i.e. you could have a charge that moves in a loop, like in this particular example, you could put a charge here and let it flow through the loop, and it would end up, when it got back to where it started, it would end up with more energy than it started with. And so you might say, well, wait a minute, how is energy conserved then if the charge can just keep going around forever and increasing its energy forever? Well, you do have to consider that this isn't a closed system. There is a magnetic field that's changing that requires energy in order to change. So it is still true that energy is conserved. It's just the total energy of the electromagnetic system is conserved, not just the electric, not just the electric aspects of the system. So now that we've resolved, or now that we have this local form of Faraday's law, now we can actually go back and resolve the issue of the solenoid inside a loop. So the paradox, just as a quick reminder, we had our solenoid inside a loop. This is a long solenoid, so it extends in both directions. And we have our loop that goes around the back. How is it that flux through that loop, flux through that solenoid and hence through the loop can induce current flow in the enclosed or in the surrounding loop if the magnetic field is actually 0? Like the magnetic field is just not, it's just 0 everywhere on the loop. How can that affect the loop itself? Well, the trick is that, and here we have that, we're assuming that the magnetic field is changing inside the solenoid because we need changing flux, right? Sorry, let me just draw this in. So what we can establish that, what we can, so outside the solenoid, B is 0, which implies that d phi dt is 0 outside. But it's not 0 inside, and that's the important part. So, sorry, that's also true, but more importantly, the time derivative of the magnetic field outside is also 0, right? If the magnetic field is 0 outside for all time, regardless of what the magnetic field inside the solenoid is doing, that means that the rate of change of the magnetic field is 0. But here's where things get funky. What this means, the fact that the magnetic field, the rate of change of the magnetic field is 0 outside, what this implies is that the curl of the electric field equals 0 on the electric, or on the loop of conductor, the loop of wire. So we're just using this local form of Faraday's law and plugging in that the change in magnetic field is 0 everywhere outside the solenoid. And in particular, the change in magnetic field is 0 along the wire, right? So this means that the curl of the electric field is 0 along the wire. But that does not mean that does not mean that the electric field is 0. It just means that it has no curl. And I mean, that's kind of obvious from the definition. But the point is you can have electric fields that still circulate even though the curl is 0. So for example, in cylindrical coordinates, so z, phi, and r, if the electric field is some constant divided by r in the phi hat direction, so this would be an electric field that circulates because it's pointing in the angular direction, then it is the case that the curl of that electric field is 0. Even though the electric field circulates, the curl is still 0, and you can check that yourself if you're curious. The way it works is that because I'm not going to go into the details, but I challenge you to check it. And so the point is this circulates. And so because the electric field circulates, that means that electric field will force current to flow in a circle. And so you'll still have some induced current, even though the magnetic field is 0 there. And that's because you can have a 0 curl, you can have a curl-free electric field while still having a circulating electric field. So it's kind of magical that this magnetic field, which is actually nowhere touching the enclosing loop of wire, nonetheless still has an influence on it. And the reason this happens is because the magnetic field is non-zero inside. So you could figure out what the change in electric field is inside. And then you just use a continuity condition. The electric field can't go from non-zero to 0 instantly as you cross the boundary. And so what you're left with is an electric field that changes that starts off non-zero here. And so if the electric field is non-zero on the edge of the solenoid, then it can't be 0 slightly further away from the solenoid. Otherwise, the curl would be non-zero, but the curl needs to be 0. And so you have to have a little bit of electric field as you move further away from the solenoid. It's just because the electric field is circulating inside the solenoid that the electric field also has to circulate outside the solenoid. So this whole business, at least to me, when I first learned about it, seemed magical. Maybe it doesn't for you, but that's neither here nor there. All right, so that's the end of, well, it's not quite the end, but we're going to spend some time applying this notion of induced currents and induced EMFs and things like that, because we're going to start talking about inductance. In particular, we're going to begin by talking about mutual inductance. Right. So before we actually do this, just for ease of drawing circuits, we need to introduce a new circuit symbol. So the symbol that we're going to see is a symbol that looks like that. So this is a variable current source. Variable current source. And the way it works is there is some function, say I of t, that this current source always spits out. It spits out a certain amount of charges every second, and the amount of charges every second it spits out is determined by this function I of t. And this current source will just produce whatever voltage it needs to produce in order to spit out that much current. So think of this kind of as like it's like the current equivalent of like a variable voltage battery. Right. So we're going to use this kind of thing a lot, so that's why it's useful to introduce. And so now suppose that we place two circuits. We have two separate circuits that aren't like connected in any way, arranged like the following. So say we have, all right. So say we have a circuit with a variable current source and it's hooked up to a solenoid or to a bunch of coils. And then there's another bunch of coils over here that's hooked up to a different circuit. They're not actually touching. And we are just measuring the voltage across that, that different loop of wires. So we have current, say, flowing upwards, determined by this function. And by the way, this function is something that like an experimenter decides. Like they program their computer to increase the current as a function of time or to make it go in a sine wave or whatever. This is something that's predefined. It's not something that often you can solve for. I mean, in principle, you could solve for it, but generally you won't have to. And so that current is going to produce, because it's current flowing through a loop of wire, it's going to produce a magnetic field in this loop of wire, right? And the important part is that that magnetic field also is passing through, and that magnetic field changes with time because the current changes with time. But the important part is that that magnetic field is also passing through our second loop. And so there is some induced, I don't know why that's so thick. Let's use blue maybe. There is some induced flux that also changes with time in that loop of wire. And let's say this loop of wire has n loops. So the idea here is that the current flowing through the left circuit produces a magnetic field in the solenoid. That magnetic field, it's a finite solenoid, so it exits the solenoid and it has to go into it has to close back in on itself, so it's not zero outside, and it'll pass through the other solenoid. And so when the magnetic field passes through that solenoid, you can then compute the flux of that magnetic field passing through the solenoid. And that flux will then also change with time. And so there will be an induced current or an induced voltage, which drives the current. If this was a complete circuit, it's not because there's a voltmeter. But anyway, so it produces some induced EMF. So just as a quick note here, the magnetic field as a function of time, the magnitude, is just proportional to the current, right? And that's because in general, in a solenoid, at least to a good approximation, the magnetic field inside the solenoid is just proportional to the current. It's mu naught times n times I, right? And so further, the rate of change, the number of loops times the flux in the second loop is proportional to the magnetic field. And that should be kind of obvious. The flux through a single loop is proportional to the magnetic field. And so if you have n loops, then n times the flux is proportional to the magnetic field. And so the important part is that both of these geometries, both of these proportionalities, they just depend on geometry. They depend on the geometry of the setup. So regardless of like how many turns there are or how big the loops are or whatever, there's going to be some constant proportionality that gives you something like this. And there's going to be some constant proportionality that gives you something like that. And so this is a lot like the whole business with capacitors. If you can write down these proportionalities such that they only depend on the geometry, then you can establish some relationships, and then given a certain geometry, you can just attach a number to it. So in the case of capacitors, given some arrangement of plates, of conductors, like parallel plates or coaxial plates or whatever, you just associate a number to that structural arrangement, and we call that number capacitance. We're going to do the same thing here, where we can relate the induced voltage, which is going to come about because the flux is changing. We're going to relate the induced voltage to the current flowing through the first loop, and they're going to be related by just a number that's determined by like the structure of the system, the physical structure. And in fact, that really just says that n times the flux through a single loop is just equal to a number, say m, times the current. This m here it's just a constant of proportionality. and it only depends on the geometry. And so we give that number a name. We call it mutual inductance. Mutual inductance of the system, right? So every system that has, two coils is going to have its own mutual inductance, and that's something that you can calculate, or that's something that you can measure. And it will depend on where coils are and the shape of the coils and how close they are to each other and so on and so forth. But the point is that anytime you have more than one loop, you're going to have current flowing through one loop influencing the voltage in the other loop by this sort of relationship. And so, in fact, we can use Faraday's law to determine the induced voltage in the second loop. Of course, the induced voltage is over here because that's the one that we're looking at. And so Faraday's law just says that the rate of change of the flux is equal to the times n is equal to the induced voltage. So really what we have here is we have that the induced voltage is equal to minus m, because there's a minus sign in Faraday's law, times di dt. And so this is the formula that defines mutual inductance. And so in particular, if di dt is a constant, like if the current is just increasing linearly with time, that would mean that the induced voltage is just a constant. And you could find that mutual inductance by just dividing the induced EMF by the rate of change of the current. So this is a lot like the magnetic analog of the equivalent thing for capacitors, where you have Q equals CV. The difference here is that these things, the curly E and the I, and the rate of change of I, those both change with time, whereas typically in a capacitor, we're only interested in, we can express that relationship just in terms of constants. Yes, this is precisely how wireless charging works. Yeah. So just a formality that we have to get out of the way, we should talk about units. Capacitance has units of farads. We should talk about the units of mutual inductance. So M has units of magnetic field times area divided by current, right? So the way to think about this is that we have an M here, right? So we have magnetic field times area is flux, and then we want to divide it by current to get the mutual inductance. You could have done it another way. We could have actually just divided voltage by current per unit time. That would have worked just as well. It's equivalent. But this is a more standard way of doing it. And when you do this, you get Tesla times meters squared, because you have magnetic field times area, divided by amperes. And we give that a name, call it H. It stands for Henry. So a system will have 5 henries or 0.2 henries of mutual inductance, just named after a guy. It's just, in this case, his last name sounds like a first name. So just as a quick note, this circuit that I drew above is reversible, meaning that if you instead swapped the location of the current, the constant current, sorry, the variable current generator and the voltmeter, you would read the same voltage even if you swap them, even if they have different number of loops and different geometry. And that might not seem obvious, but it is indeed the case that that's true. So M doesn't just describe the mutual inductance when you have current running through one side and EMF on the other side. It describes current running through either side and EMF on the opposite side, regardless of which one has current flowing through it. And we can actually show that relatively easily. But let me just write that down really quick. So the point is that M, which is equal to, which we've defined here as N times, and I'm gonna use labels now. So I'm gonna call this one 2 and this one 1, just for clarity. M we defined as N2 phi 2 divided by I1. So you have the current flowing through loop 1, and you can divide the number of loops in loop 2 times the flux in loop 2 divided by that current, and you get M. It's also true that this is equal to N1 times phi 1 divided by I2 if you had current flowing through the other one. And so let me just prove this to you by doing an example. So we're going to talk about coaxial solenoids. Right. So this is going to be hard to draw, so bear with me. So we're going to have our measuring solenoid hooked up to a voltmeter. I'll draw the voltmeter in a minute. And then we're going to have our current flowing solenoid, which is around it. You know what? I should have drawn the current flowing solenoid first. Blue is current flowing solenoid. Then we have our measuring solenoid inside. So we have current flowing through the blue one with a variable current source. And then we have, we're measuring the voltage on the black one. So this is the same circuit that I drew before. It's just now this whole circuit is inside the other circuit. But you can see that there's still going to, if there's current flowing through the blue solenoid, then you'll have flux flowing through the black solenoid. Yeah, inductors are just solenoids, and we're going to get to that today, hopefully. So we can derive the mutual inductance of the system. Let's say that blue one we're going to call 1, and the black one we're going to call 2. So the magnetic field from I1, how is energy conserved in the inductance system? We will get there. So the magnetic field from I1 can be calculated relatively easily using the standard. We know how to calculate the magnetic field inside a solenoid. So the magnetic field, B1, say, is mu naught N1 I1 over the length, say L. And so the magnetic field passing through the black coil is the same because it's just inside, and the magnetic field is everywhere the same inside the solenoid. That means that B2, or that is to say, the magnitude of B2 is just the magnitude of B1. That's the magnetic field inside the black solenoid. So that tells us what the flux is. The flux through the second solenoid is B2 times A2, which is B1 times A2. And we know what B1 is. This is mu naught times N1 I1 A2 divided by L. Okay, and so then from the above result, where we have a formula for the mutual inductance, we get that the mutual inductance is N2 phi 2 divided by I1. And so plugging in phi 2 and plugging in I1 and all that and so forth, we get that the mutual inductance of the system is mu naught N1 N2 A2 divided by L. Okay, great. So that just is the mutual inductance of the system. Now you might ask how this is reversible, because it looks like it's not symmetric, right? Like you have an A2 here, but you don't have an A1. So how could you get the same answer? And the trick here is that the reason you have an A2 there is because the area of the second solenoid is smaller. So if you instead put current through the smaller solenoid, the flux through the larger solenoid would not be the magnetic field times the area of the larger solenoid, because there's no magnetic field outside the smaller solenoid. It's just the flux through the inside solenoid. So in both cases, you end up with the magnetic field. So in both cases, you would end up with a factor of A2, and that's because A2 is smaller than A1. In the lecture notes, I do go over this in a little bit more detail. I derive it in reverse, and I'll leave you guys to look at that if you're curious, but I don't want to spend too much time on it because it's not an interesting calculation. There is a good example in the Young and Friedman textbook that I linked to as well, so take a look at that if you want more practice. Right, okay, so that's what happens if you have two solenoids near each other. And by the way, the reason we use solenoids for all of these is because solenoids are really like the easiest way to produce a uniform magnetic field that's easily calculable. That's why solenoids show up in like the only real use of magnetic fields that we have in electronics and circuits and stuff comes from solenoids, and then arranging solenoids in various ways to produce a magnetic field that we want. But right, so just because So it's not necessarily the case that you need two solenoids in order to see some sort of induced EMF, right? So if you have current flowing through a solenoid, the flux through that same solenoid is changing. So there will be some induced EMF on the same solenoid. And that gets us to the topic of self-inductance. So like I just said, in just a single coil, this effect can be observed. And so when, just to reiterate, so when current is flowing, when current is changing through a solenoid, the magnetic field on the interior of that solenoid is changing. And so the flux of the magnetic field through that solenoid is changing. And hence there is some induced electric field, sorry, some induced EMF from Faraday's law. That's just true. And so when that happens, we're talking about the solenoid self-inducing some EMF. And so that phenomena is accurately described as self-inductance. So self-inductance is defined the same way as above. It's defined as just the relationship, or it is a constant, the inductance of a solenoid, the self-inductance of a solenoid is defined as just using the exact same formula that we saw above. It's just now, instead of having two different things, one of them, we calculate the flux in one and the number of turns in one, we divide it by the current in the other. Now it's just the number of turns in one, the flux in one, and the current through the same thing. So L here is the inductance of a solenoid or of a system. It's the self-inductance really, but oftentimes it'll be abbreviated as just inductance. And it turns out that this thing, and by the way, just like mutual inductance, self-inductance is also just a property of geometry. It's derivable in much the same way. It's easy to compute for a solenoid. For like a physical solenoid, can we compute L for a changing value of I? Yeah. So in fact, the way that because if I changes, so will the flux. And it turns out that the way they change precisely cancels out, so you're just left with a constant. So the inductance for a solenoid, it's N times phi over I, which is just N times BA over I think I'm no, that's correct. So flux is just magnetic field times the area of the solenoid. The magnetic field is mu naught Ni over L times A divided by I. And so we're left with that the inductance of a long solenoid is just mu naught N squared A divided by L, where L is the length, A is the area, and so on. And so so what I was getting at from Avinash's question is that the magnetic field changes in precisely the same way that the current does. So in fact, the only thing that's changing, the current in the system, that cancels out, which is exactly what we expect, because this should just be a property of the geometry. It shouldn't depend on what current you're feeding it. So the induced EMF, so this is where things start to get weird, right? Because you have current flowing through a solenoid, but then that current flowing through a solenoid changes, and so that induces an EMF, and that induced EMF will cause current to flow in a different way, maybe less, maybe more, whatever. And so it seems like it's kind of cyclical, but it's not. And in fact, it's just like one cycle. It just happens the one time. And so let me just write a quick phrase just so I can be a little bit more clear. So the idea here is that the induced EMF inside the solenoid it acts to change the same current that caused it, that caused the induced EMF. And that seems strange, but we can use Faraday's law. So there is a flux through this solenoid, so we can use Faraday's law to figure out what the induced EMF is. We can just calculate, because we know that Faraday's law is just a true equation. So the flux, or rather Faraday's law, is a statement about the well, no. So what I'm writing is just a definition of inductance. So this is saying that N times the flux through the solenoid is equal to L times the current flowing through that solenoid. That's an I, not a phi. And so we can take the time derivative of this, N d phi dt, that's equal to L di dt. Now, L doesn't change here because it's just a constant. It just depends on the shape. And so from Faraday's law, this should give us a negative times the induced EMF. So we have that the induced EMF is negative L times di dt. So when there's a change in current through a coil of wire, that current produces an EMF across that coil of wire. And we'll see later that in fact that change in, or that voltage drop across that coil of wire can affect how much current is flowing through it. And so there can be a feedback loop. And in fact, you end up having to solve a differential equation if you want to understand how the voltage and the current change with time. Oh, by the way, when we talk about a solenoid in a circuit, this is called an inductor. Because it induces. So often you'll see someone talking about inductors. They're literally just talking about a solenoid in a circuit. Not all inductors are solenoids, but almost all of them are. So this is to say, are we going to be using any other shape inductors in this class? I mean, we could be. The shape of the inductor really doesn't matter. It just affects the inductance. So the EMF induced, so the EMF is induced so that it reduces the change in current as much as possible. So imagine for a moment, so for example, let's say that suppose that the current is decreasing. In a solenoid. So like something is happening outside the solenoid that's causing the current through the solenoid to decrease. What that implies is, I mean, that means that the rate of change of the current is negative. And so that would tell us that the EMF, the induced EMF in the solenoid, is positive. And so the way to read this, the way to understand this, is that the inductor would produce an EMF in the positive direction. Now, when we say in the positive direction, this means in the direction of the current flow. So you would have current, you have your inductor. You have current flowing this way, but it's decreasing. And so it produces an EMF that's higher up here than it is down here. And what that happens is because the voltage is higher up top than it is below, that would produce more current flow. It would produce more current flow to flow around the circuit. And so it prevents the current from decreasing. So this induced current flow bolsters the current because the current is decreasing, which causes the flux to decrease, which causes, and so on and so forth. So, sorry. So what you can think of inductors as doing is they're kind of like dampening objects or dampening devices. If the current is changing through them, the inductors will act to slow down the rate at which the current changes. They will try to oppose the change in current by either pushing current in the direction it needs to go to stay constant, or to reduce the current, to oppose the current flow so that it doesn't increase anymore. And the analogy that's used in the Liber text, and I'm not sure how fond I am of it, but the analogy that's used there is this notion of a smart battery. Like an inductor is like a battery that changes its voltage and like the sign of whether which side's positive, which side's negative, to try to keep the current the exact same, to try to keep the current from changing. Now it can't actually stop the current from changing, but it will smooth out the change in current. It will make it slower. Now there's a good example in the Young and Friedman book of a rectangular toroid. So I would suggest that you guys take a look at that. It's an interesting problem. And it will give you a sense of the kind of thing that happens. And by the way, this is why things like toroids are useful, because a toroid has a well-defined magnetic field, and the magnetic field doesn't escape the toroid. It's zero outside, as we saw on the exam, right? And so the magnetic field in a toroid is still there, and so it will still function as an inductor, but the magnetic field won't affect other components. So it's a good way to shield your circuit if you want an inductor in your circuit somewhere. Right. So that's the notion of self-inductance, and we're going to use this later. But at this point, we can kind of just abstract away the notion of solenoids to just inductors with some inductance, and they behave a certain way. That they behave a way that obeys this formula, actually. And we don't have to worry about the geometry of the solenoid anymore or anything like that. All it is just a device that behaves like that. Right. So before we continue and start talking about circuits, let's talk about the energy in a magnetic field. So remember back in the day, we talked about the energy stored in an electric field inside a capacitor. And that gave us a way to talk about the energy stored in any electric field. It doesn't have to be inside a capacitor. So it turns out that just like a capacitor, an inductor stores energy in its magnetic field. So in this case, so the question is how much energy does it store? So we were able to calculate how much energy is stored in the electric field by basically figuring out that it's exactly equal to the potential energy of the system, or it's exactly the amount of energy that it takes to separate the charges to produce that electric field. Here it's a little bit trickier, but we can figure out the energy required, or the energy stored, by noting that we know how much energy flows in or out of an inductor. So suppose that we have the following circuit. So we have a variable current source, and it's just hooked up to a solenoid, right? So because the inductor behaves like an EMF source, which it does behave like an EMF source, the power absorbed or emitted, any EMF source, the power absorbed or emitted by that EMF source has this formula, P equals IV. And depending on whether it's absorbing or emitting, it will affect the sign of P. But it's that the power, which is just the rate of change of the potential energy, really it's the negative rate of change of the work, or sorry, power is the rate of change of the work, which is the negative rate of change of the potential energy, but we're taking absolute values here anyway, so it doesn't matter. This is just equal to the current flowing through the device times the EMF, the voltage across the device. So for batteries, it was just P equals IV because the battery just has a well-defined voltage. But in this case, the EMF can change. So we have to be a little bit more careful. So let's assume, just for the sake of this example, that the current starts out at 0. We close the switch, the current's 0, and then it ramps up. And we know that it's not going to ramp up instantly, because if it did, then the inductor would work very hard to reduce that. It smooths it out. It will smooth out the rate at which the current increases. So as the current increases from 0, the EMF will act to decrease the current. The induced EMF, rather, will act to decrease the current flow. And that's because inductors, quote unquote, want to keep the current constant. And so if it was 0 before, and then it starts to change, well, now the inductor will want it to go back down to 0. And so when it acts to decrease the current, the magnetic field, in doing so, the magnetic field inside the solenoid has to increase. It has to increase in magnitude anyway. So the current is increasing, the EMF is the current is increasing, the EMF is increasing, and the magnetic field is increasing. All of these things happen in tandem. And so what we can do then is we can establish that the energy absorbed by the inductor is it's caused by the current increasing. And the reason we know that is because there has to be some energy associated with the magnetic field. And as the current increases, so does the magnetic field. And the magnetic field increases so that it can induce current it can induce an EMF to block the current flow. So this is to say that the rate of change of the potential energy of the inductor is equal to and I can drop the magnitudes here because we're just talking about, we know that they increase in tandem with each other. It's equal to the current times the induced EMF, which is the rate, which is L times the rate of change of current, right? This is just from this equation up here. And the reason, by the way, the reason why we dropped a minus sign, it does check out, and it's because the current induced is in the opposite direction, and so the minus sign checks out. Anyway, and it should be the case that if di dt is positive because the current is increasing, then we know that the magnetic field increases, and so the potential energy should increase. So this side is positive and this side is positive, so we shouldn't have a minus sign. So we can integrate to find the actual stored potential energy. So the potential energy in the inductor is an integral of du dt dt. We're just integrating from, we're integrating dt. So this is just Li di dt dt, just integrating the same thing on both sides. And so this right-hand side just becomes an integral of Li di. We're just integrating symbolically here, which is just equal to 1/2 Li squared. So this is the energy stored in the inductor. And so this is a lot like the capacitor, right? The energy stored in the capacitor is 1/2 CV squared. Here it's a little bit different because, we have current and we have inductance and so on. But you can see that these sorts of relationships are very similar, and there's a good reason for that. It's because they are indeed similar. In fact, just like we did for a capacitor, we can actually use this result to determine the energy stored in any magnetic field, right? So in a solenoid, as just established, it's 1/2 Li squared, and we know the inductance of a solenoid. This is 1/2 times mu naught times n squared a divided by L times I squared. And so now we can just do some algebra to it. We get 1/2 mu naught Ni over L quantity squared times AL. All I'm doing is I'm multiplying and dividing by 1 because these be decimal. Yeah, it could be. You could rewrite it in terms of EMF too, but you don't often. So simplifying more, this is 1/2 mu naught. And now we have inside here, we have the magnetic field. So this is B squared times AL. This term is the volume of the solenoid. And so what we get is that the energy density in a solenoid, it's a little u, is the energy in the solenoid, big U, divided by volume, which is just 1/2 mu naught times B squared. And this is a vector. So this actually tells us what the energy density is in any magnetic field. And it has a very, very similar form to the energy in an electric field. The energy in an electric field is 1/2 epsilon naught E squared. Here, it's 1/2 1/mu naught B squared. So this gets us to the relationship where if you swap, like if you want to go from electricity to magnetism, you kind of just swap all of the electrical variables to magnetic field variables. And the only thing that you do, the only thing that's different is that epsilon naught becomes 1/mu naught. And then basically everything holds. And I mean, there's a few extra things, but like these sorts of relationships, it's not surprising that mu naught appears in the bottom here. Right, so again, and we're going over this quick because this isn't, like the notions here aren't new, we're just generalizing it to magnetism. Just like how we can insert a dielectric into a capacitor to change the electric field and hence change the energy storage and the capacitance and so on, we can do the same for magnetic fields. It's just we instead insert something that behaves differently in the influence of a magnetic field rather than behaves differently in the influence of an electric field. And we already know what those things are. Those are magnets, or in particular, they're ferromagnets, paramagnets, and diamagnets. So we can talk about enhancing inductors in the same way. Right. So remember that paramagnetic material, bolster the external magnetic field. because the dipoles in the paramagnetic material align themselves with the magnetic field, which increases the magnetic field, and diamagnets reduce the external magnetic field because they anti-align, basically. Because, well, we talked about it before. Just as an aside, by the way, this is different than what we saw in the case of capacitors, and that's because for capacitors, we only saw dielectrics, and dielectrics were things that if you insert them inside a capacitor, the electric field is reduced. So dielectrics are more similar to diamagnets. There are no such thing as paraelectrics. They just don't seem to exist as far as I know, but there is such a thing for the magnetic field. So we can actually not only decrease the magnetic field in an inductor, we can also increase it. So to handle these materials inside an inductor, and by the way, when I say inside an inductor, I mean like literally you fill your solenoid with, jelly or something, just like you fill the gap in the capacitor with jelly. So to handle these, we introduce a new notion. We introduce this notion of permeability. And we give it a name, or a variable name, mu. And you might now be catching on to the story that I'm telling. So in a vacuum, the permeability is mu naught. So the permeability of the vacuum is mu naught, and hence the name permeability of free space, or permeability of the vacuum, or the vacuum permeability. So just like with electricity, if a material with some interesting permeability is present inside a solenoid or in any system with a magnetic field, all we have to do is replace mu naught with mu. If a magnetic material where mu is just the permeability of that magnetic material. And so, for example, if you were trying to use the Biot-Savart law in a system where there is, like inside a lump of iron, which has some permeability, then instead of using mu naught over 4 pi, you would use mu over 4 pi, and then you would do the integral like normal, I dl across r divided by r cubed. Or if you were doing Ampere's law, say inside a lump of iron or inside a bowl of water or whatever, Ampere's law just becomes mu times I enclosed on the right-hand side. So using material properties is relatively easy. You just kind of swap in the appropriate permeability. I mean, it's designed to be that intuitive, right? So just as a quick note, let's think about what happens if mu is different. So for example, from the Biot-Savart law, we see that if mu is larger than 1, then we would see that the magnetic field, if mu is larger than mu naught, then the magnetic field increases, or the magnetic field is larger. It's increased. And so we know what that tells us. We know that paramagnetic materials increase the magnetic field because they align themselves with the magnetic field. So that implies that when mu is greater than mu naught, the material is paramagnetic. And we know that when mu is less than mu naught, for the same reasons as above, it would reduce the magnetic field. And so that would mean that the material is diamagnetic. Just like we did for electricity, we introduced this notion of the dielectric constant kappa. We can do a similar thing here, introduce a notion of magnetic susceptibility, that's a tongue twister, magnetic susceptibility, which is just another way of characterizing the magnetic permeability. it's basically a measure of how different your permeability is from the vacuum permeability. Magnetic susceptibility. Susceptibility. And the variable that we ascribe to magnetic susceptibility is a chi. It looks like a curly X. It's a Greek letter, chi sub m. And it's just defined in terms of the magnetic permeability. So mu is 1 plus chi sub m. Let me make that m a little bit more distinct, times mu naught. So this just says that if you have a positive magnetic susceptibility, then you have a paramagnetic material. And if you have a negative magnetic susceptibility, then you have a diamagnetic material. And this is just, it's a number between -1 and infinity, effectively. So you can decrease the magnetic susceptibility or the permeability to close to 0, but you can't get to 0, or you can increase it to however big you want. So that is to say, greater than 0 for paramagnetics. For paramagnets, chi sub m is less than 0 for diamagnets. It's just kind of it can be a more intuitive way of understanding these things because it separates positive and negative values to the two different types of objects. Right, okay, so that's everything there is to know about materials properties in inductors. Obviously, it's not everything, but that's the basic gist. We know how paramagnets and diamagnets behave under the influence of magnetic fields. And so you can characterize, just as a materials property, iron has a susceptibility or a permeability of this number, and plastic has this number, and water has that number, and you can just go out and measure these things. Okay, so now that we've talked about all the different ways you can change the magnetic field and all the different ways you can measure the energy in a magnetic field, and we've talked about inductance and self-inductance and mutual inductance and all that, now we can actually just start working with circuits. We have the physics understood underlying. Now let's start just shoving inductors into circuits. So let's start with LR circuits. And I don't think we're probably not going to get all the way through today, but we'll get as far as we can. So before we begin, I just need to introduce the last circuit symbol that we're going to use in this course. And that is just the symbol that represents an inductor. So it's often drawn like this, or sometimes it's drawn like this, or sometimes it's like it's drawn like an actual solenoid. But they're all the same. It's just a picture of an inductor, right? Or a picture of a solenoid. Oh boy, what just happened? Okay, it just represents an inductor. Not SSR, but LR, what? I don't know what that means. So before we can actually just start solving problems, we haven't really understood how we represent or how we handle inductors in a loop rule, right? We know a way to figure out how to handle figure out what the EMF induced on an inductor is depending on the way the current is changing and so on and so forth, but we don't really, we don't know the rule. How do you know when you add or subtract or whatever? So the way we're going to do this is the way we figure out a lot of things. We're going to use an example. And for a lot of these, you have to determine what side of the inductor is positive and what is negative just from thinking about the circuit, just like how you have to for a capacitor. If the capacitor starts out empty, how do you know which side is going to be positive and negative, which will affect whether you add or subtract Q over C, right? You kind of just have to think about the way the current's flowing, and you have to imagine that charges are accumulating. Now, if you guess wrong, that's still okay. You'll just be everything will just be different by a minus sign. And you'll still get the right answer, but you have to assume a current direction. And in the case of inductors, you're going to have to assume the way the current is changing. Is it increasing, decreasing, whatever? So we have our battery, have a switch, we have our resistor, and then we have an inductor. Actually, I'm going to use the loopy kind because It's more obviously not a resistor. So the inductor has inductance L, the resistor has resistance R, battery has EMF E. So when the switch is closed, if the inductor weren't present, the current would go immediately from 0 to, from Ohm's law, E over R. It would go from 0 to E over R immediately, or instantaneously. Now that is a large change in current, right? In fact, it's an infinite change in current because it happens instantaneously. But because the inductor is present, we know that the inductor will act to oppose the change in current. It will act to slow it down, to prevent it from changing as much. And in doing so, it induces an EMF. The inductor induces an EMF in the opposite direction. Because it's trying to prevent current from flowing, because it wants to slow down the current flow rate. I'm going to put opposite direction in quotes. So let's use Kirchhoff's loop rule. So using the KLR, Kirchhoff loop rule, clockwise, we would get that, so we pass through the battery, we get plus EMF because we're going from negative to positive, passed by the resistor, minus IR because the current, we're going to guess that the current flows clockwise. And then we have to add the change in voltage across the inductor. So that is really the voltage difference. We take VB, we subtract it from VA. So VB minus VA is what this delta V is. And this should be equal to 0. Now there's no externally applied magnetic field that's changing, so this really just is 0. We don't have to worry about extra stuff on the other side. So the question is what is the change in voltage? What is VB minus VA across this inductor? So when the current increases from 0, or it increases from right to left, so through the inductor. So the current would flow from right to left through the inductor, right? According to our guess. So when the current increases and it's flowing from right to left, from Faraday and Lenz's law, I'm just going to abbreviate Faraday Lenz, indicates that the induced current, so the current is increasing from right to left. So in order to reduce the current, you would have to have current flowing in the opposite direction. So you would want to have, it would induce an EMF that has a positive sign over here and a negative sign there. So current would want to flow in the opposite direction, right? Oops. That's from Faraday and Lenz's law. Right, indicates that the induced current or the induced EMF is to oppose that increase. So the EMF is greater on the right, or I should say, so the voltage. So the voltage is greater on the right than on the left. And that's because if you just let that inductor have higher voltage on the right than the left, then that means that current would flow counterclockwise rather than clockwise. And so, so the picture here is you have your inductor with current flowing this way, but it induces a voltage that's oriented that way. So that means, and we also know the magnitude of the induced voltage, the induced EMF, that's just equal to L times di dt. That's just from the definition of L. And so when we go around the loop clockwise, the voltage on the right side of the inductor is higher than on the left side. So we get a negative contribution. The voltage decreases as you go around the loop. the voltage drops across the inductor. And so our formula then becomes E minus IR minus L di dt equals 0. So that's what our differential equation becomes, or our loop equation, which is a differential equation. And by the way, this does not mean that you always put a minus sign next to the inducting term. It depends on the system. It depends on what's happening, how current's flowing, whether it's just starting up or whether it's constant and then it's decreasing or whatever. It very much depends. And so you kind of have to go through this thought process to think about what direction, if current was flowing this way and it was increasing, what direction would the inductor produce an EMF to counter that change? So by the way, this equation, it might look scary, but this is actually basically the same differential equation that we used in a charging RC circuit. It just has different variables in different places, but like it's the same structure. You have a constant term, you have a term proportional to the thing we're solving for, and then you have a term proportional to the derivative of the thing we're solving for. So we can just solve it using the same methods. And we get that the solution is I of t is e over r times 1 minus e to the minus t over tau, where here is L divided by r is what tau is. So here it actually looks a lot like a charging circuit. And in this case, it really is. You're charging the inductors in the inductor's stored energy. The magnetic field in the inductor is increasing as the current increases, and it charges up. So by the way, just as an aside, in an LR circuit, higher resistance lowers the time constant. And we can see that here. If R is big, then tau is small. And what that means is it means that you have if you have a higher resistance, then you have faster decay. And that shouldn't be surprising. If the current goes from 0 to 5 amps instantaneously, that's a bigger change than if the current goes from 0 to half an amp instantaneously. So the inductor will have less of an effect in cases where the current decreases by less. So the picture, just to complete this idea, the picture of this of the current, or a graph of the current with time, looks something like this. And it looks exactly like a charging capacitor, where here this asymptote is at E over R. Now, just as a quick note, it does not, the current, because of the inductor, the current does not increase does not increase at an infinite rate initially, like it would if there was no inductor. Instead, the slope is just E over L. So in fact, as you increase L, what you're doing is you're decreasing the slope. So larger inductors will slow down the current more. Up here, by the way, the slope approaches 0. And that's because if as you wait a longer and longer time, let me back up. So there's a feedback loop happening here between the induced voltage and the induced and the current, right? And so once the inductor starts working, it will slow down the rate of change of the voltage, or it will slow down the rate of change of the current. And if the rate of change of the current decreases, that means that the slope of the current function is smaller. And so what's happening is that the inductor becomes less and less effective as time goes on, because in doing the inducting thing, it is reducing the thing that makes it work to begin with. So inductors, if you wait long enough, just stop doing anything. It doesn't quite fill up. Well, it kind of does. It will fill up in the sense that it will just have a constant magnetic field after a long time. Yeah. Well, okay, no, because if it was an equipotential, yeah. Well, okay, yes, it does become an equipotential as long as the current remains constant. But it doesn't stop current once it's filled up. It just lets current flow through for free. It doesn't block current. When inductors are empty, that's when they block current. It'll block current from increasing. If it was at 0, then it'll stop the current from increasing instantly. After a long time, you can just set di dt to 0, and the current will just be E over R, like in this plot. And by the way, there's another good, there's a whole page of examples and things like this in the Liebert or in Young and Friedman, so I suggest you take a look at those. We could also look at a similar circuit where you have, say you have an established current flowing through a circuit, and then all of a sudden you open it, or you make that current instantly go to zero somehow. Like you remove, maybe you have a, maybe it's this circuit, and then somehow you immediately replace the battery with a wire. So now instead of having current flow, now you just have what would be zero current flow. In that case, the inductor will act to try to keep the current up. It will try to prevent the current from going to zero. And so it will use up its magnetic field to try to produce a current that keeps flowing in the same direction. And it will eventually decay away, just like a discharging capacitor. In that case, the current, or the current obeys the exact same formula. It obeys a formula that goes, that is exponentially decaying, just like a capacitor. It has the same time constant as we found here. It's tau is L over R, and so on. And again, this is in the this will be in the lecture notes that I post tonight. Right, so that takes us through to the end. So we will end right there.